Today, I'm talking about geometric quantization and the convergence of metric measure space. So until yesterday, I have explained the notion of the convergence for pointed metric measure spaces and the convergence of spectral structures. And today we apply it to our situation, so situation of geometric quantization. Okay, let's start. First of all, I want to explain the setting of today's talk. Let X and omega be a closed symplectic manifold of dimension 2n, and let L, H, nabla be prequantum line band. And we assume that the Lagrangian torus fibration is given. Let mu be a smooth map from X to B, and this is Lagrangian torus fibration. Torus fiber bundle. Torus bundle, sorry. And we suppose that one parameter family of omega compatible complex structure, which is asymptotically semi-flat family, is given. This is asymptotically semi-flat omega compatible complex structure. Family of okay. So asymptotically semi-flat implies that J is converging to mu as S to 0 in the sense of polarization, and I have assumed some more assumptions. And in this case, in fact, if we suppose Js is asymptotically semi-flat, then we can show that the Ricci curvature of Js is bounded by some constant kappa independent of S. I don't prove this, but we can say that the existence of the lower bound of Ricci curvatures. Next, we put let S be the unit circle bundle of L, and denote by G hat Js the connection metric on S. And now we define that a point in B is called MBS fiber. Here, M is a positive integer. B is called MBS fiber if this is a definition. If Lm, we restrict Lm to mu inverse B, and we also restrict the connection to the fiber of mu B, then this line bundle over mu inverse B has non-trivial parallel section. then B is called MBS fiber. So I have already defined that Bohr-Sommerfeld fiber, Bohr-Sommerfeld point. I should call it MBS point. And the fiber, mu inverse B is called MBS fiber. So I have already defined that Bohr-Sommerfeld point. So one BS point is the Bohr-Sommerfeld point. Then you can check that if B is MBS fiber, MBS point, then it is also L times BS point for any positive integer L. Moreover, I say that B is called strict MBS point if B is an MBS point and B is not LBS point for any L less than M. Now we have the next theorem. Let B be a strict MBS point and take U from S on mu inverse B. Then there exists some constant, some positive constant C, such that the metric measure space S with dg hat js and the measure is mu g hat js and normalized by C square root of S to N. And the base point is U. Then this pointed metric measure space converges in the sense of S1 PMGH topology as S to 0 to some metric measure space denoted by S0M, D hat 0M, and mu hat 0M, and the base point U0M. Here, I should explain what is this, the limit space. And this is the sense of S1 PMGH. So we have the S1 action, isometric S1 action on S, and we also have the isometric S1 action on the limit space. So this topology is the pointed measured Gromov-Hausdorff topology with S1 equivariance. So I'd like to explain what is the limit space. Here, S0n is this is not independent. This is not dependent on M. In fact, this is direct product of S1 and Rn. And here we have S1 action, the natural S1 action defined by E2 IT and X times E2 I theta is E2 IT, plus M theta with X. This is the S function. So as a set, as a space, S0M is not dependent on M, but the S1 action is depending on M. Here we have M. Then we put an Riemannian metric G0M by this dt square over M square 1 plus the square norm of X plus sigma the square of dxi. This is a metric on S1 times Rn. So this is the Euclidean metric on Rn, and this is a metric on S1 direction. Then from this Riemannian metric, we have the Riemannian distance, and I denote it by d at 0m. This is the distance appearing at the limit. Next, the measure is not Riemannian measure. Measure is, in this case, dt dx1 to the dxn. This is nu hat 0m. So this is not dependent on m. And the base point is the pair of the origin, the unit of S1 and the origin of Rn. This is the base point of the limit space. So I don't prove this in this session, but I prove it. I want to explain the proof in the next exercise class on today's afternoon. But I cannot explain the proof of the general case. But I'd like to explain the proof of the simplest case. But it is the simplest case is essential. So I'd like to explain the simplest case on this afternoon. Okay. Then we have this S1 PMGH convergence. Then by the result, which I have explained yesterday, we have the strong convergence of the spectral structure as follows. We have the following strong convergence of spectral structure. L2S with measure mu g hat JS over C root S2n tensoring C and taking the invariant space by the representation rho k, and we consider the operator delta Laplacian G hat JS rho K. Then this converges to the spectral structure associated with the limit space of appearing here. The spectral structure introduced by this limit space. So it should be L2 S0n tensor C log K and delta 0n log K. So delta, this operator is this is weighted Laplacian given by the metric G0m and the measure mu0m, mu hat 0m. So this Riemann metric and this measure gives the weighted Laplacian, and I denote it delta 0m rho K. Now, we can see that we have shown that this spectral structure is identified with the d-bar Laplacian acting on L2K. So this is the Hilbert space is L2 with X with LK. Sorry, the notation is confusing, but this LK is this L is prequantum line bundle. Sorry. So this means that the L2 sections on L2K. And the operator is, this operator is identified with 2 times d-bar Laplacian acting on Lk plus constant k square plus kn. I have shown it. These two operators coincide, and I have shown it in the second session. So what I want to show that the spectral structure defined by this. So this is converging to L2 S0 n tensor C log K with delta 0m log K minus K square minus Kn. Okay, then next, I'd like to explain what is this spectral structure. Now put BSK equal a subset of B consists of KBS points. And let BS0K be the subset of B consists of strict KBS points. Then, if we denote by lambda k, the set of the divisors of k lambda k is the set of positive divisors of k, and then we may write BSK is the disjoint union of M in lambda k and BS0 M. Now we have the following proposition. If M is in lambda k, then this spectral structure is identified with L2 with on Rn with the measure E2 minus k, the square norm of x dx. The ddx means the Lebesgue measure, and we have this weight, and we tensor C. We are considering the C-valued functions, and the operator is delta k Rn, and which is defined by using the standard coordinate minus ddxi square plus 2k xi ddxi. This is an operator, the differential operator on Rn. And this is a weighted Laplacian on this Gaussian space. This is a Euclidean space. The distance is given by the Euclidean metric, and the measure is given by this Gaussian measure. And then if we consider the weighted Laplacian, then it is nothing but this operator. Moreover, if M is not in lambda k, the first case is the case of M is in lambda k. So M is a divisor of k. And if M is not a divisor of k, then we can easily to see that L2 is 0M tensor C, and taking the invariant subspace is 0. Of course, this space is not 0, but taking by considering the invariant subspace by the action rho k, we can easily to see that only the element is 0. Then combining these results, so we have shown that theorem 2, we obtain theorem 2, and we obtain the spectral convergence. So we denote this spectral convergence by asterisk. Then by applying Theorem 2 and the spectral convergence for every Bohr, k Bohr-Sommerfeld point, then we obtain the next strong convergence. We have L2 x Lk with 2 d bar Js k converging strongly to the direct sum of the next spectral structures L2 Rn with Gaussian measure tensor C with the weighted Laplacian on Gaussian space. Then the next theorem is main results of my talk. So let I write this convergence 2 asterisk. The convergence is, this convergence is compact convergence. This is the main result. And I want to explain the key lemma to show this main theorem later. But before showing it, I want to mention some remarks. So, this type of theorem holds also for the following cases. So now I have considered, until now I have considered that the Lagrangian fibration has no singular fiber, but we can show that the type of theorem for the case of the Lagrangian fibration of which has singular fiber. The one of the result is when X and omega is smooth, compact smooth toric variety. And this is also shown by Yamashita and me, where mu is the Lagrangian fibration. Mu is given by the moment map of toric variety. So associated with the torus action. And we take JS such that torus invariant tending to the large complex structure limit. But I should mention that there are some difference between the case of toric variety and the case of non-singular Lagrangian fibration.
I'm sorry, could you comment what is large complex structure limit? Could you say a few words about that? What do you mean by large? What do you mean by large?
This is, I don't mention it, but so for the toric variety, the omega compatible torus invariant complex structure is described by symplectic potential, denoted by GS. And so the symplectic potential is one of the function on the delta polytope, and so matrix valued function, and this is symmetric matrix valued function. And taking, we may write by the language of, if we use the language of symplectic potential, then GS can be written as G0 plus some, S inverse with A, and A is positive definite, some positive definite symmetric matrix. And if we take S to infinity, then it becomes bigger and bigger, and this is called large complex structure limit.
Thank you very much.
Okay. Then, so in this situation, we have the type of theorem for the toric variety, but in this case, the limit space is depending on whether B is in the interior of the delta polytope or in the boundary, or B is in the boundary of the delta polytope. So if B is in interior, then the limit space is S1 times Rn, as like the non-singular case. But if B is in, for example, if we consider that X is CP2, then the delta polytope is this triangle. Then if we take B from this vertex, then the limit space becomes S1 times R half line, the direct product of a half line. So like this. So limit space depends on whether B is in interior or the boundary, or so if B is in this edge, then the limit space is S1 times half line times line. This is the difference. And the second example is the case of K3 surface. So I cannot explain the precise statement, but let omega 1, omega 2, omega 3 be hyperkähler structure on X, and we fix it. K3 surface is a 4-dimensional closed smooth manifold. And then we can see that X with omega 1 is closed symplectic manifold. And I assume that the homology class represented by omega 1 over 2 pi is in H2 XZ. And then omega 1 has the prequantum line bundle. And we also suppose that X has elliptic fibration, but elliptic fibration means that the holomorphic map to one-dimensional complex manifold, and here it is CP1. And so we regard X as a complex manifold with respect to I3. Here, since X is hyperkähler, so we have three complex structure I1, I2, I3 corresponding to every symplectic form. And we regard X as the third complex structure. Then I assume that we have, I assume that the elliptic fibration is given with respect to this complex structure. Then the singular fiber of elliptic fibration on K3 surface is classified by Kodaira. And I assume that the order of the singular fiber are of type I1. So this is this is focus type singularity, singular point, which is appearing in Miranda-Stoke. So every singular fiber has only one focus singular point. Then we can see the number of singular fiber is equal to 24, which is equal to the Euler number of X. Then this is assumption. Then there exists some family of hyperkähler structures on X. Here, but this family depends on S, but omega 1 and omega 2 is independent of S, but omega 3 depends, only omega 3 depends on S. But in this case, the metric and the complex structure, hypercomplex structures are depending on S. So I1S, I2S are depending on S. And we suppose, such that omega 3s, if we integrate omega 3s over mu inverse b, then it is converging to 0 as S to 0. We can take such one parameter family of hyperkähler structures. Such family always exists. Then by taking these complex structures, one parameter family of complex structures, we can show the spectral convergence of the prequantum line bundle. Then we have the theorem for in this case. And in this case, we have, in this case, the limit space is independent of whether B is critical or regular value. Of mu. These are the remarks. So I'd like to explain the proof of theorem 4 outline. So theorem 4, the compact convergence is shown by the next key lemma. Let Fs be a function on S and it satisfies that the L2 norm of Fs is 1. The L2 norm is normalized, and suppose that the supremum of the L2 norm of DFS is this L2 norm is with respect to G hat S, and this is the same. And the supremum is finite. This is assumption. Then for any positive real number epsilon, there exists positive S0 and positive constant C, such that for any S, positive S less than S0, the L2 norm of Fs on the neighborhood of BSK points is not less than 1 minus epsilon. This is the key lemma. It may be complicated. So this means that intuitively, this means that, for example, let Fs be the eigenfunction on G hat JS, and we suppose that for example, for the simplicity, let Fs is eigenfunction and eigenvalue is written by lambda s, and then this condition means lambda s is bounded. Lambda s is bounded. Then we can show that the L2 norm of Fs is concentrated on the neighborhood of the singular fibers. Sorry, singular, not singular, Bohr Sommerfeld fibers. So here is B, and here is BSK point, KBS point. These are KBS points. Then if we take BS, family BS, then, and taking S to 0, then this is Fs. Then it's concentrating on the neighborhood of KBS points. This is the meaning of this lemma. And proof of this lemma is inspired by the result by Furuta, Yoshida's work, which is the study for the localization of the index of Dirac operators. So we compute the L2 norm of DS2. Then it is G hat JS and DFS, DFS, and the measure D mu G hat JS. Then this is, we estimate it from below by this integral. So we consider, we restrict DFS to the fiber of mu inverse B, mu inverse X. And so we use the action angle coordinate and decompose into the angle direction and action direction. And we replace this term by this term, this integral. Then we can show that, then we check that we observe here, and we estimate it from below by the fiber-wise operator, some fiber-wise operator. This is this operator is some differential operator on defined on every fiber, and we can estimate the eigenvalue. Estimate the lowest eigenvalue of this operator, and it is estimated by estimated below by estimate the lowest eigenvalue by the distance of X between X and KVS point set. So we can see, we can show the lemma. This is the idea. Now we have theorem 4, and the theorem 4 is states the compact convergence, and compact convergence means the convergence of the d-bar Laplacian. So from this, we can show the convergence of eigenfunctions, eigenspaces. Eigenspaces. Let PS be the orthogonal projection from the L2 sections of LK to the kernel of d bar JSK. And this is nothing but the holomorphic sections of LJK. And the first aim of us is to study the asymptotic behavior of this vector space. This is our main goal. This is our goal. And let P infinity be the projection defined on the limit space. So L to Rn with Gaussian measure to kernel of weighted Laplacian. And this kernel consists of constant functions on Rn. So this is one-dimensional space. And let these operator be the orthogonal projection. Then by Shioya, we can define the notion of the convergence of these operators. We can define the convergence, strong convergence of this operator. Then let K is positive. Then we have, now I am considering that the case of the fiber of mu are all of the fibers are non-singular fiber case. Then we have the strong convergence of these operators. And this corresponds to the convergence of the holomorphic sections to the Bohr-Sommerfeld fibers. And this is given by, this theorem is given by Theorem 4. But we should remark that, and we have to also show, and we have to show the non-existence of the family of eigenfunctions such that if we denote the eigenvalue by lambda s, and we normalize the L2 norm of phi s to be 1, and we should show that the non-existence of phi s such that lambda is converging to 0. So if such phi s exists, then maybe there exists a sequence not contained in this space, but converging to the 0 eigenvalue of the limit space. So we have to exclude this possibility. But it can be shown by we can show it by the spectral gap result of Diva operator, Diva Laplacian. Spectral gap that is, we can show that the spectrum of d bar Js k is contained in 0 or the numbers larger than or equal to k plus kappa. Here, kappa is the lower bound of the Ricci curvatures. And in this case, we can see that kappa can be taken as sufficient. We can take kappa sufficiently close to 0. So we can prove that the second eigenvalue, so the positive eigenvalue is greater than 0. So we have the spectral gap. Okay, so it's time to stop. Okay, yes, okay. So I'd like to stop here. Thank you.
Thank you very much. Are there questions? So doesn't seem.
Sorry, I don't have a question. I have a comment.
Yes.
I want very much to congratulate Professor Hattori with an excellent lecture course. Thank you very much.
Thank you.
I have one question.
Yes, please.
If you are given a covariantly constant section on
Yes.
a Bohr-Sommerfeld fiber,
Yes.
can you extend it to a holomorphic section? You prove the convergence of holomorphic section to localizing along the Bohr-Sommerfeld fiber.
Yes.
My question
Yes.
is in the opposite direction. If you are given a covariantly constant section along a Bohr-Sommerfeld fiber,
Yes.
it's something like Osawa-Takekoshi theory.
I think it is yes, but so the answer is okay. So if you take the covariant parallel section on one Bohr for some Bohr-Sommerfeld fiber, then we can take the holomorphic section on denoted by phi s. So which is this is 0, and such. So you are saying whether this phi s goes to the given Bohr-Sommerfeld fiber. Yes, I think it is yes.
It is certainly asymptotically yes.
Yeah.
In the asymptotic sense.
Asymptotically.
You think that it is yes without asymptotic.
Yes.
It is. I see. Thank you.
Are there more questions? So it doesn't seem to be the case, but we have an afternoon session for the exercises. So we meet again in half an hour. The Freiburg guys have coffee and the rest probably breakout rooms or just a break. So let's thank the speaker again.
Thank you.